So, first of all, this is joint work with my PhD student, Jan Bracker, who very recently defended his dissertation on this stuff, and very successfully so. So, of course, you're all familiar with monads and related notions, and they have had a profound impact on how we write functional programs, being able to reconcile purity with effects. Okay, so there are lots of different effects and lots of different monads for different effects. Lots of different. There's language support, of course, in Haskell in particular, the notation. Lots of different supporting libraries, and so on and so forth. So lots of stuff out there, but it's not quite the end of the story so far. Okay, there are lots of things, notions out there that look like monads, but they are not quite monads as we understand them. And if you were here this morning and you saw Simon PJ's talk, towards the end you saw a variation of the IO monad that wasn't a monad. And as it happens, that is a so-called graded monad. Okay. But there are many more of these that people have found or stumbled upon depending on specific needs, and so on and so forth. And it's all a bit annoying that they're not quite monads because it doesn't fit them with the infrastructure that we have. But before we get there, let's just see here what kind of things that are out there that people actually have been using for writing real programs. So we have our standard monads, of course, and you know what they look like. This is usual binary term there. And then we have this thing called graded monads. And what happens here is that we add an index to the type constructor. And for the graded monad, this index is an element of a monoid. So you have then some kind of monoid operation, and you use this to combine that thing there with that thing there into the index of the resulting computation. Okay, it was exactly what happened this morning, where we had this this number essentially that was combined. There's also something called index monads. The name is perhaps a bit unfortunate. It's also called Hoare monads. The idea here is that you can think of, there are two indices now, and you can think of them as some kind of pre and post state. Okay, and then you see what's going on here is that the post state of this computation is the pre state of that computation, and then overall, of course, we have this pre state and that post state in the result over here. So the usual sequencing going on there. And of course, in the case of return, I didn't say that, but for graded monads, we just get the neutral element there. And in the case of index monads, the state doesn't change. Okay. And then there are constrained monads, when we want to sort of impose some kind of constraint on the return types of the different monads. We want them to be in some particular type class for various reasons. Some use cases of these things, just quickly. Graded monads, we already saw one this morning. More generally, information flow control, composable effects, index monads, composable continuations, session types was mentioned as well this morning. Constrained monads, quite often in domain-specific languages, they pop up because we want to constrain the kind of types we deal with in our language, and then quite naturally we want to have a constraint on the monads. Quite common. And just to give you a little bit more concrete example, so here is an example of session types. And we define some very simple protocol. We can read and write, and we can say when we are done. And then we can define a simple protocol here. We say, well, in this case, we want to read an integer, write a string, and then we are done. And now we can then have operations in our monad, where we say, well, in order to do a write operation, we have to be at a state where the protocol says, yes, now it's time to write. And for reading, the protocol needs to say, yes, now it's time to read. And then when we run things, well, we want to make sure that whatever we run is going to end up in the done state. Okay? So then we can sort of enforce this protocol. And when we compose this write and read and so on, we know that the program we write will respect the protocol we have defined. So that's a very naive example of a session type, I suppose, but even so. And then you see then, in this case, what we get is this index monad, or the Hoare monad, where we have this idea of pre and post states and being through in the obvious way. Okay? So, what's the problem now then? Well, of course, you can already program using these kind of generalized notions, just as long as you have a sufficiently powerful type system, as you do in GEC with extensions, for example. So that's okay, but and you can even use something like GEC's abandonable syntax to use the do notation for your new things if you want to. So that's cool as well. But of course, each generalization, they come with their own type class. It's a bit different from the standard type class and a bit different from each other. And that has a lot of consequences. And furthermore, if you want to combine these things, maybe you want something which is both a graded and an index monad, for example, you need another type class. Okay? And that means that all these libraries that we have out there for doing monadic stuff, they no longer work because they, of course, use the normal monad type class. So we need to re-implement all this stuff to use the new things we want to have. And if you want to use more than one kind of monad in a single module, then things becomes really tedious because you have lots of same named operations, and you can no longer rely on the usual overloaded machinery to sort of just make it look nice and convenient for you. You have to explicitly say, now I want to use this, now I want to use that, and your do notation is inevitably only going to work for one of the monads, and you have to do something else for the others. So it becomes rather messy. So the idea then, of course, and this is not a new idea. People have been looking at this problem before. I just want to, I'm going to come back to that later. But the idea is that, well, obviously, it would be nice if there was a single notion that could cover all these bases, not rocket science as such, right? So if bind had a type more like this, okay, where instead of insisting on the same type constructor in all these positions, we say, okay, let's this be one thing, and that another, and that thing a third, then you can see that this could be instantiated to all these different cases we saw, the graded monad, the indexed monad, and any combination of these as well, or anything else you might dream up, pretty much. Okay. So in particular, here is the bind for the graded monad, and you can see that we can sort of here instantiate that m to that other m there, apply to I, and here we have that n would be that m applied to j, and that p would be that m applied to the combination of I and j. So that would be good. And how can we do that? Well, let's introduce a class called bind then, a 3-parameter type class, where we overload the bind operation in the obvious way, like this. Okay? Now, an immediate consequence of this is, of course, that well, in the usual Haskell monad class, it contains both the bind and the return. But now we need a separate class for return because return only mentions a single type constructor. So we now need a separate class return like this. Okay. So we are forced to tear them apart like so. Okay, this looks promising. What can we do with this? Well, we need to do a bit more things first. So if one look at the sort of categorical foundation of this, as Jan did, one will realize that, well, actually all these things, they should be functors, and also in practice, you want to be able to say that you want certain constraints, impose certain constraints on these indices in your monad. So the actual class we ended up with looks like this, where we insist that m, n, and p are functors, and what we only give the program an opportunity to impose certain constraints on these constructs as well. Okay. And the class return looks like this, same story. We want the m to be a functor, and we want to have the possibility to impose constraints on that m. Default, there are no constraints, and sometimes you have to just leave it at that, but you can impose constraints if you need to for your particular application. Now, I should emphasize here, and I'll come back to this point, this is not yet general enough to capture the idea of constrained monads, because remember, in constrained monads, the constraints are on the, let's go back to the previous slide, the constraints are on the return types, result types, the A's and the B's here, As you see, the A's and the B's are not mentioned here. So this is not yet enough to capture constrained monads, but we get back to that point in a bit. Okay, well, you know that monads comes with laws. What about these supermonads? Do they come with laws? Well, yes, they do. And the nice thing is that the laws are exactly the laws you know and love. They look exactly the same, at least at this level. The types, of course, will be more defined. But the laws themselves are intuitive and what you're used to. So that's a nice, yeah, good to know. Nice that doesn't become more complicated than that. Now, what's the caveat then? Well, it turns out that if you just do what I just said, and you then try to write some code with this stuff, you'll get into deep trouble very quickly. Well, not trouble, but it turns out it becomes very inconvenient because the types are too liberal in a sense, so everything becomes very ambiguous, and the GEC will say, sorry, your program doesn't make any sense to me, or rather it makes too many senses. I can't tell which sense you mean, and therefore I'm not going to compile this for you. You have to sort of tell me what you mean by adding annotations. And there'll be an awful lot of annotations to add, so much so that it's not very attractive at all. Just to give you one example, suppose we use the maybe monad in this setting. We write a little snippet like this. So we have just 3, and then we continue by binding that 3 to a j here, and then return 4 plus j. We would expect this to type check and be or type just int, right? But instead, GEC will come back with something like this. We say that, well, we have this thing of type p_int, where p has to be in the class return, and then we have this that bind maybe n and p must also hold. And the problem, of course, is, okay, so maybe later this p will be constrained to something concrete, but there is no hope at all for the n, right? So GEC will refuse this. Oh dear, what do we do then? Well, actually, there is a bit more to Supermonad than what I said. So not any instance of the type class you saw is a valid Supermonad. We want to impose some more structure on these guys. We want to say that for things to be a Supermonad instance, there must be exactly one bind and one return instance for every Supermonad base constructor. And furthermore, the constructors of the bind instance must all be partial applications of the same constructor. Like you saw, for example, in the graded index monad, right? There was always the same guy applied to various indices, and that's what we want here. Okay. But of course, and if these requirements are satisfied, the ambiguities go away, and that's good news. But obviously, the type class I showed you doesn't tell this story at all. And maybe there is now a way of making GEC to capture this. I don't know. GEC is a moving target. When we looked at this, there was no way to sort of explain this in Haskell code. So what did we do? Well, we turned to writing a plugin instead. So our take is this, and I'm not saying this is the answer really. This is a bit of a pragmatic thing, but we want to be able to experiment with this and work with it and see how it feels and what it looks like, and maybe eventually something better will come out of this. Anyway, what we do is this. So we view bind and return as special classes in an extended Haskell language. Okay. And then we implement this extension through a GHC type checker plugin. And this plugin will enforce the requirements you saw on the previous slide. Let's go back to this again, just to remind you that there has to be exactly one bind and one return instance for every base constructor. And when we instantiate bind, then the 3 constructors of bind are all part application of the same base constructor. So the GEC plugin enforces this. And then it can exploit this additional knowledge it now has, thanks to enforcing this, in order to help us with the type checking and type inference. And as I said, these requirements are enough to bring us back to essentially familiar territory. You can write the code you usually write, and it will type check OK without any funny ambiguity error messages popping up. OK. So I said what I showed you wasn't enough to capture constrained monads. So what do we do if we want to have constrained monads? Well, we can do the obvious thing. I said, well, the constraints should be on the result types, the A's and the B's. So all you have to do then really is to add the A's and the B's to the bind constraint, and then you can express constrained monads. So that seems good. So why don't we just do that then? Well, unfortunately, this has some knock-on effects, which makes the framework somewhat cumbersome to use. In particular, the types now of functions that are polymorphic in the supermonad, they become quite unwieldy. Okay, I will not show you an example, just that's unfortunately the case. It becomes a bit cumbersome to use. Okay. So what we have done right now is we say, okay, we are going to give the programmers both versions of this type class, one that supports constrained monads and one which doesn't, so that people who are not interested in constrained monads, they can use a simpler class and then write their code and hopefully be happy and gain some experience and give us feedback on that. Whereas those who need the constrained monads, well, they will use the more complicated class and they have to pay the price, unfortunately, for doing that. Okay. Again, as long as the monads are not polymorphic, or code is not polymorphic in the monad, then things are fine. But when they are polymorphic in the monad, it becomes a bit unwieldy, in particular than with the constrained monads. Okay. So that's what we do, and it's not an ideal solution. But again, we view this as a sort of a stepping stone to allow us to explore this space, and hopefully, at some point, some better solutions will come along. Okay, I mentioned applicatives before, and you'll be pleased to know that applicatives can be generalized in exactly the same way. So we have something called super applicatives. It's also part of these libraries. And here you see the class definition. Again, this is the one that does not support constrained applicatives, but just the basic ones. But exactly the same story applies here as for monads. Yeah, so exactly what you would expect. So we have, again, we insist on M, N, and P being functors. We have a way of allowing constraints on these indices if the programmer wants that. And then you have the usual application operation there. The return class is shared with Supermonads, so there's just one return class. You might have observed that applicative is not a superclass of binding. You might wonder why that is so. Well, or you might say, well, it should be. And we would say, actually, we don't think so. But it's a point I can discuss. So here is our position. So even for normal monads, some people, including me, think that maybe it was a bit of a mistake to make an applicative superclass of monad, because quite often you don't really care about the applicative instance, you only care about the monad. In this setting, the case is even more compelling because there are two ways to characterize an applicative, through which operations you put into the class definition. And normally they're completely equivalent, but in this setting, when we have constraints, they are not completely equivalent, as it turns out. So in some cases, one formulation is useful and the other one is significantly less useful. And then it seems to us that it would be unfortunate to pick one notion and making that then the superclass and then force people to use that particular notion if it turns out that that notion is not very useful for them. So therefore we say, okay, maybe there should actually be two different applicative classes, one for each notion, and people should be able to pick whichever makes sense for the particular applicative. But we certainly don't want to force them to use one or the other by making one of them the superclass of monad. So we didn't. But of course, it is the case here that we have a shared notion of return between these two, between applicatives and monads. So in that sense, it's like we right now have in Haskell, with the where return is just another name for pure. Okay, I mentioned other approaches. You might have heard about polymonads. So polymonads goes back a fair few years now. And in fact, polymonads is where Jan started looking at this problem, and he implemented polymonads for Haskell, so we get some practical experience of using them. They are more general than supermonads in some ways, but as it turns out, the ways in which are more general doesn't seem to be used in real code data. We looked very hard, all kinds of code using extended notion of monads, and we couldn't find any example where this more general, the additional generality of polymonads actually were used. So polymonads, when they were used, seem to be used for things like index monads and graded monads and that kind of stuff. Okay. But they are more general in that sense. However, in some other ways, they are more restrictive. In particular, the indices for polymonads, they have to be phantom indices, and that rules out a lot of use cases. Okay. So that is when we took half a step back and said, okay, well, we like the basic ideas of polymonads, but maybe they're a bit too general, and then we impose these extra constraints of the bind operation having the same type construct being partially applied, and that sort of all the constructing the bind operation and so on. So, so we were able then to define supermonads so they capture the use case that we have seen in use actually, and then also then we relaxed. So for supermonads, the indices can certainly, they don't have to be phantom, for example. Also, we couldn't see how to do constraints polymonads at all, but for supermonads, that was in principle straightforward, even though it becomes a bit clunky, as we discussed. Finally, the laws for polymonads are quite different from the usual monad laws, and I'd say a bit tricky to get your head around. So it's nice then to find that the supermonad laws are, well, the usual ones. There is also Edvard Kmet, wrote a library that influenced us, certainly, and there are many similarities. What he did not do was that he tried to use function dependencies to get rid of all these ambiguities, with some but not total success. So if we have actually tried to use both his library and our in a number of use cases, in a number of sample cases. And it turns out that if you use Kmet's libraries, you have to add annotations a lot more than what you need to do with supermonads and with the help of the plugin then. So we found that it was easier to use the supermonads than Kmet's libraries, but they are certainly quite similar in many ways. Okay. And his stuff predates ours. Okay. Want to use this stuff? Can you? Yes, absolutely. They are on Hackage, package supermonad. You can get the source from GitHub. And they work with GHC from 7.3 up to 8.4.2. At least that's what Jan tells me. And he's actively maintaining this. So I think it will keep working for the foreseeable future. So that's cool. And what do you actually need to do if you want to use this stuff then? Well, you do this. If you want to use the do notation, you enable rebindable syntax. And then you activate the type checker plugin in the way that Gabe described earlier today. Yeah. And then you import control supermonad prelude, so you get a standard library tailored for supermonads. And then you implement your supermonad, whatever your supermonad of the day might be. Okay, and that's it. It's really quite straightforward. And when you write the code, as I said, thanks to the plugin, you should be able to write the code pretty much as you always have, and you shouldn't notice much difference in terms of having to add extra annotations or anything. It should just work. We have tried this on legacy code, and essentially you have to do the obvious things of changing the monad instances and so on. But when it comes to type checking the code, including monad transformers and stuff, it just works. So in that sense, I think it's quite successful. I'm going to wrap up with giving you an example, sketching an example. I'm not going to give you any lots of code here. But we're going to look at how we can use this framework to implement a safe version of Banker's algorithm. So this is an algorithm used to Dijkstra, and it's about avoiding deadlocks in a concurrent setting where you have a fixed set of resources. So for example, a deadlock can happen if you have two processes, A and B, and there are two resources, X and Y. And both A and B need both X and Y. And then say A has X and B has Y, and then they both require the other one. And then, of course, you're stuck, right? And what Banker's algorithm does is that it allows us to avoid getting into that kind of situation. How? Well, the idea is that each process has to declare its maximal need up front. So in our scenario, A would have to say, I am going to need both X and Y. And B would have to say, I am going to need both in X and Y too. Okay? And then whenever a process requires a resource, the resource allocator will make a check, knowing what the declared needs of the processes are, and say, okay, if I were to give you this resource, knowing what everyone currently has, is there still a way to run all the processes to completion if the worst case scenario occurs when all the processes require the rest of their needs? And if there is such a way, then it's safe to give the process what it wants. Otherwise, it's going to have to wait for a bit. Okay, so that's the essence of Banker's algorithm. Of course, this only works if the processes are truthful, if they honestly declare the maximum need. Okay? And they might not. Even if we are not sort of malicious, it might be that we have edited the code and sort of added the request somewhere, and we forget to say that actually now adding this particular resource request means that we have to up the need and declare this increased need. Easy to forget. So what we're going to do then is we want to keep track of this need automatically in the types of processes. And we can do that using a graded monad. Okay. Indexed monad first, and then we're going to use a graded applicative at the next level up. So the indexed monad is going to be like this. We have two indices. We have the pre-state, which is a pair of the maximal resource need so far, and the resources held prior to this action. And the post-state is then the new maximal need and the resources held after the action. And then afterwards, we're going to lift these into graded applicatives, because applicatives, in principle, allows us to run these concurrently. So we're figuring out the maximum needs, and then we say, okay, now we have these processes with known maximum needs, and then we say, okay, run these as concurrently as you see fit, in the way you'll see shortly. So just to give you an idea what it's going to look like, so we are going to have then operations for doing claiming and releasing of resources. And you can see here that what's going on. So pros, then is this indexed monad. And here is the before state, okay, with a maximal need of a resource A, and the current allocation of that resource B, and the maximal need of a resource B, and the current allocation of the resource B. And then when we claim an A afterwards, well, the new max is going to be M of A and the successor of R of A, of course. And we are going to have one more A being held here, whereas MB and RB, but these two guys are untouched because this was only concerning the resource A. And release is like this. we start with we need of course to have at least an A to release. We have a successor of RA there. And having released it, we now have RA left of that resource A. And the maximal need didn't change. And then here is how we can lift this into a graded monad by this process constructor. And it basically says, well, initially, the maximal need and what they hold is 0, both for A and for B. And in the end, we are going to have a computed maximal need, MA, and a computed maximal need, MB. But also all the processes have to have released all their resources of type A and type B, like so. Okay. And then we get something we can call exec, which is this element of the graded monad, graded applicative, with the pair of the maximal needs here in the type index. And now we can just combine executable processes with the applicative operator. And then, of course, the combined maximal need, when we do this, is just going to be the max of the two of the indices for the two combined processes, because we could always run them sequentially, right? And therefore, the max is the max of each individual one. And it's up to the scheduler to decide whether to run them sequentially or not, but at least we know statically that, indeed, if you just take the max of these guys, well, that is the max that we need to consider for these guys. So the scheduler then may decide to schedule them concurrently or not, but that's sort of a bit of a side issue. So that's a sketch of how we can use a indexed monad and a graded applicative together in this framework to express a safe banker's algorithm. Yeah, and that was pretty much all I wanted to say. Okay, there are some papers if you're interested. And there is one long paper that's currently being considered for a journal, and then there is sort of a slightly earlier paper from the Haskell Symposium a couple of years ago. Okay, and they're all available off my webpage. Thank you.
Great. I think we've got plenty of time for questions.
Yeah.
So Henrik, I was wondering if you could tell us a bit more about the type inference story, what your plugin does, because I think obviously, if you stand back and look at it, you'd prefer not to have class-specific inference rules if possible. So, on reflection and looking at the way that you do, maybe you can tell us a bit more about what are the extra inferences that this plugin makes that the built-in system does not. I mean, I'm thinking a bit like functional dependencies give you a certain sort of extra inference. Is there a mechanism you could add to the language generally that would allow you to express the stuff that your plugin does in a way that would work for maybe other classes, not just the ones that you've thought of here?
I mean, that's what we would like.
Yeah.
I agree.
So
I agree completely. This is a bit of a workaround, no doubt.
So
we couldn't find right now. We couldn't find, because if you go down the
what does it do, the plugin? Can you tell us any more about that?
What it does?
Yeah.
Well,
what extra inferences does it make that are not standardly made?
It's simply this. Well, simply, but in essence, it's this. It enforces these constraints on the instances for bind and return, right? And by having enforced this, it will know that when it comes to a code like this, for example, instead of being lost here when it sees maybe there and then sort of just some arbitrary type constructor there, some type of constructor there, because it enforced the rules you saw on the previous slide, it will know this has to be maybe as well, and that has to be maybe as well, and we're back into familiar territory. That's in essence what's going on.
So it's a bit like functional dependencies, isn't it? So you could say that maybe the second and third parameter are determined by the first, but they're not completely determined, that's what you're saying. Just the head is determined.
Yes.
So maybe you want a sort of head determinable version of functional dependencies. Or
that would
like
solve the problem, I think. Yes, potentially. Yeah.
And that's all it does?
Pretty much. I mean, you should talk to Jan about this, really. But In essence, yes. But you're right. It's a workaround, and you would like to have some kind of more refined notions in the language to explain these kind of constraints, if one thinks this is the right way to go. Yeah.
Do you also have a generalization of monad transformers?
As I said, at least for the usual, I don't think we have a library for it now, but the ideas of monad transformers still work in this setting. So we had code, a compiler as it happens that uses a lot of monads and monad transformers, and we then just ripped out the standard monads and plugged in this framework, instantiated it to normal monads, and it just worked with the transformers and everything. So it does work with transformers, but I don't think Jan implemented the libraries to support nothing like MTL, nothing, just the standard library, yes.
Just got one over here, and then I'll come back over that.
Going back to the thing about functional dependencies are directional, right?
Yes.
So they're given this, I know that, but actually what you have here is not directional, right? Because given any one of these three things, given the head of any one of these three things, you can get the head of any of the other ones.
Yes, and of course you can do that with functional dependency in principle. You can sort of say, if I know this, I know that, and you can do it all the way around. But if you use functional dependency for doing that, you quickly end up in not allowing anything, really. So you get just the basic monad back.
Yeah, I mean, what I'm saying is
over-constrained.
This seems more specific than functional dependencies because it's not directional.
Yeah, I mean, we don't know the answer to what an appropriate language mechanism should be, so that's an interesting research question.
So you first showed the slide with all the different kinds of monad generalizations. My first idea to generalize some of these notions was to instead use a category as a way of indexing the things. So, for example, if you have the, I think it was index monads, where you have these two indices.
Right.
This can basically be done by having the category of natural numbers with morphisms just being pairs, right? Where you a number, so a morphism from I to j is just a pair ij, and then you can compose them simply if they match up, right? You can compose ij with jk, for example. And I think this would at least generalize all except constraint monads.
Possibly. So it sounds to me as if you're talking about that you would, as a programmer, need to encode what you want to say in a particular, perhaps unfamiliar setting. That might be a price you're willing to pay. But here, I think this is quite natural to use because you can just write down the monads that are in your head, essentially, in the obvious way, and you don't need to know any categories here or any particular clever encodings to do this. But yeah, of course, if you have one way of capturing all of this that's attractive in its own right, I agree. So that could be a different way of solving this problem, potentially.
So in your associated type family, why was the kind of constraint and not star to constraint, or the defunctionalized version of that?
Oh, we should talk to John about this.
Okay.
Yeah.
Okay, any more questions? Okay, let's thank the speaker again.
Thank you.